So let me thank the organizer for organizing the nice conference and invite me to give a talk. My talk is based on this paper this year I wrote with a student. Okay, so let me begin with some introduction. We know ADS safety is very deep idea relating to seemingly different theories. We'll consider the most familiar example, like type 2B string theory on ADS phi times S phi and n equals 4 Siegel-Young-Mills. So we know that this correspondent has many interesting applications, for example, in condensed matter physics and QCD. But the precise quantitative test, usually we consider supergravity approximation, and then you say the gauge theory is strongly coupled. And so usually you need to look at some kind of supersymmetry protected quantity, like the spectrum correlation function of BPS operator. So my motivation is, can we go beyond the supergravity limit in some kind of a stringy regime? Because this is usually not much technical tools on the string theory side. So usually people kind of give up and say the Young-Mills theory is like a non-perturbative definition of string theory. But there's one particular situation, so that is, this is really the physics can be studied. This is the so-called Penrose limit of type 2B string theory. Okay, so this is proposed by Penrose in a very long time ago in the 70s, and he said any space-time you can take such a limit, so we can take this ADS space, and you get what you get is what you call a PP wave background, or some people call plane wave background. So also with maximum supersymmetry, this is the geometry. Here, mu is a parameter measure the space-time curvature and the Lemon flux. So mu equals 0 is just the flat space. Okay, so unlike the ADS space, this string spectrum can be the free string spectrum can be solved in the Lycon gauge using the Green-Schwarz formalism. Is similar to the flat space. So this is seen easier than the ADS space. So this is something that in when I do my PhD, that Berenstein, Matazena, Nestes in 2002, they proposed the class of near BBS operator now known as BMN operator. So then the free string spectrum is correctly reproduced by the gauge interaction as the planar conformal dimension of BMN operator. So this appeared, well, this limit, you look at a sector of the Young-Mills theory with large R-charge scales like square root of n. So this seems to be the right limit because a small charge does not give string interaction, but a large R charge is too strong, may blow up the string into some kind of deep ring or giant graviton. So this is a very interesting limit because in this case now dual theory can be either free or weakly coupled. This is seen a little strange because usually we say ADS safety is strong, weak duality. So there's some price to pay here that the space-time become very highly curved. And actually, I will consider the case this space-time is even infinitely curved. So this seems a bit strange, so I give some more physical motivation. As we know, a main goal of the theory of quantum gravity, like string theory, is to understand the physics in regime beyond the reach of classical gravity, for example, in some highly curved space-time region near black hole singularity. So for ADS space, if the radius of ADS space is very small, then the space-time is highly curved. And of course, some people are thinking about this. Then, but for me, the easier problem is this PP wave background. Now the curvature, it's a bit different. The scalar curvature actually vanished, but the non-vanishing component of Ricci curvature is proportional to the parameter mu square. So we actually focus on the mu goes to infinity or infinite curvature limit, what you call it. So certainly the effective action of classical gravity completely is not valid, completely breaks down in this case. But this is not necessarily a bad situation because we can like instead probe the fundamental nature of space-time. So this, well, to tell a classic movie, that I have a feeling that we are not in Kansas anymore. This is a very different regime from the classical gravity. But of course, since the background is maximally supersymmetric, then this is still quite amenable to study then, for example, the black hole singularity, Big Bang singularity. So this, of course, the point is with the helps of holographic duality, we can still study the physical string amplitude with some, of course, with some reasonable conjecture and also some constraint like unitarity. Okay, so the Penrose limit actually also provides some, there's a new twist holographic story. As is well known in the ADS-CFT holographic dictionary, the CFT lives at the boundary of ADS space and local operator coupled to the boundary configuration of ADS space. So you can vary with respect to the boundary configuration and compute the correlation function of local operator in terms of the effective action of ADS gravity. However, this geometry, the PP wave background is quite different, so it's not clear. And we are also in a stringy regime. The classical effect gravity is no longer valid, so it's not clear how to directly apply this dictionary, particularly in situation with finite string interaction. So our approach is to consider the free gauge theory. And this, as I mentioned, can respond to the infinitely curved PP wave background. But there are still some interesting finite string interactions. Okay, so since the string spectrum is completely degenerate, and there's a various interesting phenomenon that is about this called tensionless string, because all excited string have the same energy. So they can just jump from one excited state to another state. So without energy cost, and of course through a quantum unitary transition. There's well, the coupling constant is this so-called finite genus counting parameter J square over n, which is finite when both J and n goes to infinity. So we will try to compute the physical quantity on both sides and find some non-trivial agreement. Well, of course, originally the free string spectrum is given by the planar conformal dimension There's some more tests that I call the entries of this, what I call the PPW holographic dictionary. So I proposed 3 entries of the dictionary. Well, one is this planar grid-point functions that can respond to the cubic vertex of the green swatch, like a cubic vertex. And then the second dictionary is what I call the factorization formula that you can just pasting together to construct string loop diagram with this cubic vertex and compare with higher genus BMN correlation function. This first 2 dictionary you can compute on both sides and have a direct test. More recently, I proposed another dictionary that I call the probability interpolation. So this dictionary only have indirect evidence, particularly the non-negativity of the 2-point function. But I think this, since this third dictionary is most interesting, that I will mostly focus on this third entry in this talk. So let me introduce some notation. So the vacuum operator is this single trace operator where you take a complex scalar. Well, there are 6 real scalar in the n equals 4 super Young maps, or 3 complex scalar. We take one of the complex scalar and take a trace operator, and then this is called the vacuum. Then you can put in the 4 remaining scalar and sum into the trace with phases. And this gives you the BMN, so-called BMN operator. So the notation is the positive and negative mode represent the left moving and right moving excited modes of this is a closed string. So we have level matching condition that all mode sums to 0. Of course, you can also have 0 mode. This is represent a discretized momentum. The excited strings, they have at least 2 string modes. Now we can compute the correlation function. You can choose a proper normalization so that at the planar level, this means the genus, the planar genus 0 that is orthogonal. And at the higher genus, this proportional to this power of genus counting parameter. For example, genus 1, you can divide it into 4 sector and contract accordingly. And for genus H, then you divide it to 4 times H sector. So now this, what I call the probability interpolation, is when you compute the 2-point function, you find they are always real and symmetric. There's a summation formula. You sum over one set of modes, then you get this nice formula. This can be straightforward, easily proved using some kind of Poisson summation formula. Now we define this sum over all genus contribution with a kind of proper normalization. This is actually the all genus formula of the vacuum correlator, so that it looks like, now it looks like a probability distribution. That's why it's called probability interpretation. However, to interpret this as a probability, that they must be non-negative. For the case of 2-string mode, the non-negativity can be easily proven. Basically, this because the 2-string mode are opposite number due to the level matching conditions. However, for the case of 4 string modes, that it turns out it can be negative. So we don't have a clear understanding. One of the heuristic explanation is this is probably too cloudy, because for 4 string mode, you need to fully occupy the 4 transverse direction that is with unbroken SO4 symmetry. So it seems the most interesting is the case of 3 string mode, because 2 string mode is too easy. 4 string mode is no longer valid. So 3 string mode seems most interesting, but we are not aware of a simple analytic proof. But we can explicitly track the non-negativity up to genus 2. So now this suggests what I call the entry of the holographic dictionary. This 2-point function with proper normalization should be equals to the norm square of quantum string amplitude. This operator U is a unitary operator, describe a unitary transition between the degenerate tensionless string. And now the single string form a complete Hilbert space basis of the Hilbert space. They can, under such string interaction, they can just jump from one state to another. Now this caveat that, of course, probability interpolation only requires that this total contribution is non-negative, this matrix element. But we make this stronger conjecture that this is actually non-negative separated at each genus. Basically, this is inspired by also the case of 2 string mode. We conjecture it also true for the case of 3 string mode. So let me give some more explanation. This equation seems quite simple. Why didn't I thought about this only recently? But it's because it turns out that the physical picture is, well, we are in a very special space-time with infinite curvature and infinite flux. So it's quite different from usually what you're familiar in flat space or even ADS space with large radius. In particular, well, usually in flat space, you consider the scattering matrix as matrix, but here there is no finite physical process of multiple particle or string scattering to and from asymptotic region of space-time, because the higher point function always, if you take the strict and goes to infinity as we are doing here, then this higher point function always vanish. But of course, they are still somewhat useful that I will explain later further. But now the only finite physical quantity is the 2-point function. So this describes the process of this string just directly jump from one state to another. This is the analogy of the S matrix that we're familiar in flat space. But you may say, why don't we identify the 2-point function just with the quantum transition amplitude on the string theory side? The reason is that they are always real and symmetric, and you know, well, we can make it more careful that a rigorous proof that this real and symmetric matrix element you cannot be identified as a unitary matrix. So the unitarity roots out this possibility. So the otherwise seemingly most natural conjecture is the 2-point function equal to the unknown square of the quantum transition amplitude. Of course, there's some indirect evidence. Okay, so let me go give so probably I go over this part a little quickly. There's some technical calculations. So for genus 1, this 2-point function, you can write down the formula with k, any number of k of string mode. So this basically come from this diagram I drew earlier. This phase shift is the shift of string modes. So you can easily prove this formula is actually real, and you do a complex conjugation, and after a simple transformation, you see it's real and symmetric. Now for the case of 2-string mode, that this is this factor become a product of like a 2 complex conjugate factors. So it's apparently non-negative. So this is proof for, and it also works for any higher genus. This is genus 1. But so for the case of 2-string mode, then we can prove that it's non-negative for any genus. Okay, but for the property that but for any number of string mode, that is always real and symmetric, but the non-negativity is not so easy for if you have more than 2 string modes. To study more string mode, we need some standard integral. So this is just the integral that this argument will be some integers, so that they could be degenerate. So there's so I don't go into the technical details here. They can be calculated by some recursion relation. So we can write a 2-point function in terms of this kind of standard integral and compute by computer. So for example, the case of 3-string mode, first you can consider what we call the generic case. There's no degeneracy in the arguments of the standard integral, namely that none of this mode number is 0. Then in this case, you can write the genus 1 formula. Of course, you can now see it's manifestly positive. And you may ask, what happens if some of these numbers are 0, this numerous, there are possibly numerous degenerate case. And we also check quite carefully, there's several cases that is actually quite somewhat complicated, but we, in the end, the upshot is we provide a complete proof that for genus 1, this is always non-negative. Now about genus 2, then now it's more complicated. There are 21 diagram, basically this permutation of 1 to 8. They can be divided into 4 groups. It's important to go through this very complicated, laborious calculation, because while the motivation is you can say the genus 1 is too simple. Maybe the non-negativity is just a coincidence, but so it's important that we go a little bit higher and track the genus 2. And we used some symmetry to simplify the calculation that I don't go into the details here. And then we are not able, to prove this analytically. So then we have a formula that we can put into computer to track numerically. For example, for some small number, you can check the results are always non-negative, and we can also perform some random test more than, for example, more than 1 million times of more number in all these tests. They are non-negative, so we can this gives you some confidence that these two-point functions are always non-negative. And for the case of large mole number, generic mole number with large epsilon value, you can actually also have analytic formula that the leading terms are positive. Well, I can do fourth string mode, but first the five string mode. For the case of five string mode, the calculation is actually easier because for the odd number of string mode, there's some properties that this make it quite simpler. We can come for the generic case, we have this formula that it turns out that can be either positive or negative. But what about fourth string mode? Fourth string mode, then we can do only compute the genus one is already quite complicated. This 10 can be written into the 10 types of standard integral. Well, the upshot is for the case of fourth string mode, the results can be either positive or negative. So the probability interpolation is no longer valid for the case of fourth string mode, but we can also check the other entries of the what I call the holographic dictionary earlier, this factorization formula and comparison with the cubic vertex. So first of all, the cubic vertex, you can you compute the free planar free-point function with fourth string mode. But as I mentioned, that the higher point function actually always vanish in the strict and goes to infinity limit. It's perceived as a kind of a virtual process. But its ratio with vacuum operator is actually finite. You can compare with the Green-Schwarz cubic string vertex. For the factorization formula that you can compute the torus two-point function and compare with this kind of a one loop diagram, and we've checked this is valid also for the case of fourth string mode. And the cubic vertex is was first computed by Spyron Walovich, and we considered, well, and it become much simplified in the infinite curvature limit. And we check, and of course, originally in the flat space, there are some other important physical quantities, such as so-called the prefactor and higher order contact interaction. But in our case, that when we take this infinite curvature limit, it seems the only relevant quantity is this cubic vertex, and we can compare the cubic vertex with the free planar three-point function, and verify that is true also for the case of fourth string mode. And well, there's some issue that I had discussed, that we assume that the multiple string mode are in different transverse direction, but there will be some problem that if the string mode are in the same direction, probably I should not go into the details here because it takes too much. This is quite subtle and it takes some time. Basically, because this, if you put the modes in the same direction, is the vacuum, the zero mode is no longer the a BPS operator. So this may give rise to some issue. But the upshot is that some entries of dictionary are still valid, and while the probability interpolation would give some problem. So I should probably go over to the conclusion. So the PPA background has, well, there's a transverse direction naively. They have the, if you look at the metric, they have the SOA rotational symmetry. But because of the Lemon flux, they are broken to SO4 times FO, SO4. In holographically, they are described differently. Is the scalar insertion or covariant derivative as proposed by the BMN paper. So it's actually reasonable to expect our proposed dictionary to face some challenge if you have more than 4 string modes, because this would, the infinite flux would separate these 2 types of string mode. But what we found is quite surprising, that even for the case of 4 string mode, the 2-point function can be negative. So the one of the entries of the proposed dictionary, the probability interpretation, may no longer be valid. On the other hand, we confirmed that this other entry, for example, the factorization is still valid for 4 modes, while the comparison with cubic string vertex is even stronger, that you can actually see that they are, well, this is one of the problems that is too strong, that it seems that it's valid not only for 4 string mode, but any numbers of hypothetical number of string modes. So naively, you will expect they will be bounded at least by the dimension, a dimension of the background, but it's the mathematical structure is quite strong, that it's valid for any hypothetical number of string modes. So now you ask, since the probability interpretation is not valid for 4 string mode, what's the physical meaning in this 2-point function in this case? Because it's always, as I mentioned, they are always real and symmetric, so they cannot be naively identified with a quantum transition amplitude on the string theory side. So the physical meaning in this case is not so clear, but at least for the case of 2 string mode and 3 string mode, this I think the meaning is clear. There's no problem. So in my previous paper, I explained that this actually genus expansion is actually this very peculiar feature. This genus expansion is convergent. So this is quite different from most example of quantum theory or quantum field theory or string theory in flat space. Because in those cases, usually we say the perturbable expansion is asymptotic expansion, is has 0 radius of convergence, but here I have a convergence series for any finite string coupling constant. Well, this actually easy to understand, because it's the probability interpolation that is means that they sum over to 1, and they also each term is non-negative, so it's actually obvious that they should be convergent. So so then a conjecture is probably this is a very rare example. Probably we have quite lucky to find a rare example. Maybe this is already a perturbative series is a complete string theory that we don't need non-perturbative effect. So if our conjecture is correct, then this will not only provide the first example of systematic calculation of higher genus. Well, this is some kind of, although it's quite different from flat space, you can still say it's a critical superstring amplitude, maximally supersymmetric background with infinite curvature. And also in principle give exact result for any string coupling. Well, probably I give some more explanation. I mostly work on the gauge theory calculation. There's of course no much technical abstraction. You can, for free gauge theory, you can calculate at any genus as you want. However, on the string theory side, we cannot do too much. So most progress people use this RNS formalism in flat space, and it's quite difficult at genus and there's also some progress in pure Spinner formalism that I'm not an expert in this aspect. So our conjecture, maybe I can just show this. This is the probability interpolation that two-point function is the norm square of the string amplitude. So if our conjecture is correct, and you give the norms of the certain critical superstring amplitude, include all genus contribution. But there's a caveat, of course, that the string amplitude as a quantum amplitude, they are complex. They have not only the norms, but also some phase angle. But we can use unitarity to, in principle, determine a large part of the phase angle, but not completely. But initially, I was a little bit too optimistic that I thought the unitarity can completely determine the phase angles and the string amplitude. But this turns out it's not true, but not completely if you have to do a careful analysis. So this provide a long-term motivation. Probably this is not an easy problem that usually people consider flat space, but what I need here is string theory on highly curved space with flux, and also you need to include this highly excited string state in order to have direct verification of this conjecture, and also, of course, complete determination of the string amplitude. So far, what I have done is give some indirect non-trivial evidence. And of course, a technical problem is that for the case of free string mode, that we only track the non-negativity numerically, but it's of course better to have analytic proof. Although the integral are completely elementary, but it seems that while we have do many calculations, but we are not aware of simple analytic group. Probably this requires some advanced mathematical techniques. And this is also a comment about Hagedorn temperature. Usually we know that string theory has the Hagedorn temperature inverse proportional to string length. Since here my situation is quite extreme that because it's effectively infinitely long, so the hackathon temperature is actually 0. So, but of course, this is not necessarily a problem, but it's interesting to see whether we can study some interesting thermodynamics. So finally, a final comment is widely believed that, well, this basically from the second string revolution that we studied is non-perturbative objects like D-brane and M-brane that is usually believed that string theory is actually not a theory of string. String may not be the right fundamental degree of freedom. But if our conjecture is correct, on the contrary, that since we have found of course, this is a very special setting with infinite space-time curvature and the monomer flux, but still maximally supersymmetric, that this tensionless closed string do provide a proper complete degree of freedom for any string coupling constant. So we can, in other words, we conjecture that we have provide an exact non-perturbative solution for string theory, at least in this very special setting. Of course, this is a very highly unrealistic situation with infinite space-time curvature, but the hope is this may provide some insight for the general background. Thank you. That's all.
Thank you, Minxin, for an interesting talk. Are there any questions for Minxin, either on the chat or just unmute yourself if you have any question?
I have a question.
Oh, Samir, please, of course.
Hey, thanks for a nice talk. If you have a string theory that's perturbatively complete,
Yes.
does that mean that there are no open strings and D-branes?
Well, that's the conjecture. Yeah. So because it's the evidence is because the perturbative series is convergent. So I don't need.
Yeah. So, but do we have any understanding from the geometry? Like, what happens if you try to cut the string? Why is that not possible?
Because they are infinitely long. So this is very special situation. The geometry, the usual geometric picture is no longer valid. That I see, because as you see, there's an infinite curvature. So this is very special situation. Yes, indeed. But of course,
there must be some reason. Sorry.
Yeah, of course, I cannot prove there's no other correction.
Yeah. But also from the boundary state point of view, there must be something that rules out these. I mean, if you have closed strings, you have boundary states.
Yeah.
You would naturally get D-branes unless there's something which says you should know.
Well, if from the usually in the textbook, if string theory, you say you cannot only have open string. If you have open string, you must have closed string, but you can have only closed string, but not open string. This can be a consistent theory. Yeah, that's you read from Puchinsky or this textbook. Yeah.
Okay, thanks.
So building on Samir's question, perhaps, because of your tensionless limit, Minxin.
Yes.
Sorry if the question is a little bit vague, but do you get any? Do you have any understanding on the symmetries, on the representations of the states in this tensionless limit?
Symmetry.
What I'm having in mind very vaguely, so I apologize, is that if I know that in your context you have this Ramon flux, so I don't know what may be happening, but in some other context, I may think of some kind of a BMS symmetry, like in null infinity in flat space. when strings get very close to the horizon of a black hole, they also tend to become tensionless. And in the gravity side, you may try to conceive the idea that you get some BMS symmetry. So I was wondering whether, if in your limit, sorry, this is just in case that you have observed any kinematical statement in your amplitudes or something.
I'm not aware of
Okay.
this kind of symmetry, but of course the background geometry has this, of course, the rotational SOA.
Yeah,
symmetry.
sure, right.
But of course, when you take the infinite curvature limit, this geometric picture is probably not no longer valid. Yeah.
I mean,
So,
I guess that another way of saying what I was saying, but it may not be applicable to your case, is that from the wall-sheet perspective, you get this Virasoro structure, but when you take the tension of the string to infinity, the Virasoro structure gives you a BMS structure. That's a mathematical statement. So I was wondering whether this degeneracy that you were finding in your excited states that allows you these transitions, whether there is some secret BMS symmetry. But this is maybe just a remark for you to consider. I have not thought about it, so apologies.
Yeah, probably it's interesting to consider.
Yeah, I don't know. Are there further questions? Sorry.
Yeah, I have another question.
Oh, Sanjay, please.
Hello. Yeah. Yeah. So very interesting, Minxin, this positivity that you are finding with this 2-string and 3-string states.
Yeah.
Very intriguing. I was wondering, so you're thinking about a probability interpretation. Now, from the gauge theory side, basically you have these multi-trace states. Well, multi-trace operators, by the operator state correspondence, the multi-traces are some states. Naively, I would have thought that the overlap is more like an amplitude, and maybe the squares, appropriate squares, would be giving probabilities. Have you thought about that kind of interpretation?
So this is well, this, as I mentioned, there's a very counterintuitive picture here, that because if you take a multi-string state and you compute the like the 3-point function, higher point function, they actually vanish in this strict, and it goes to infinity limit. So how do I see this? Do I write somewhere other 3-point function? I didn't write the formula. Okay. Yeah, so they are actually always suppressed in the strict and equals to goes to infinity. The only finite thing is this 2-point function that they because you are taking the BMN limit, that they are proportional to the genus power of genus counting parameter. So
but within I think I could ask my question, you know, within the setup of 2-point functions, could you does it make sense to interpret sort of the squares as probabilities rather than the 2-point functions themselves?
Well, well, that's what I interpret as
okay, that's
the amplitude of square, but because it's well, as in quantum mechanics, you know, the square is the probability.
So from that point of view, it's not a problem if some of them are negative, right? Or maybe I misunderstood something.
It would be a problem if this is negative. Yeah. So that's why I say for the case of 4-string mode that I don't have a clear understanding. It's only valid for, I only propose for 2 and 3 string modes.
I see. Okay, I'll follow it up maybe by email.
Yes.
Okay.
So probably there are some more details in the paper. Yeah.
Okay, great. Thank you.